Hi students, in this video I'll be going through the 2017 O-Level Additional Mathematics Paper 2 Question 8b. So I'll use this question as example to explain why sometimes it's not sufficient for us to use the second derivative test to determine the nature of the stationary point. Okay, so let's read the question. So the equation of a curve is y equals to 8 minus 2x plus 1 cubed. So explain why the curve only has one stationary point and why this is a point of inflection. Okay, so we know that at the stationary point, the gradient of a curve is 0 and hence dy dx will be 0. Okay, so if we want to explain why it only has one stationary point, when we set the dy dx to 0 and solve for x, we should be expecting only one answer. Okay, so let's solve this first part of the question. Okay, so y equals to 8 minus 2x plus 1 cubed. Okay, so this expression is not difficult to differentiate. So differentiate 8, you get 0. Okay, differentiate this negative 2x plus 1 cubed, you need to use the chain rule. So the power comes down. Okay, reduce the power by 1. And always remember for a chain rule, you need to differentiate inside the bracket. So differentiate 2x plus 1, you will get 2, right? You multiply the 2 behind. So you get negative 6, 2x plus 1 squared. Okay, so this will be your dy dx expression. Okay, so if we let dy dx to be 0, so what we are trying to do is to find the x coordinate of the stationary point. Okay, so let dy dx equals to 0. Okay, so if negative 6 times 2x plus 1 squared is 0, it has to be the 2x plus 1 squared that is equals to 0. Okay, and if 2x plus 1 squared is 0, it means that 2x plus 1 has to be 0 because only 0 squared can give you 0, right? So if you solve it, okay, so indeed we only get one value of x, right? So now we can conclude or explain why there's only one stationary point. Okay, so what we can say is that since there is only one value of x when dy over dx equals to 0, the curve only has one stationary point at x equals to negative half, right? At the point at x equals to negative half. Okay, so we have done the explanation for the first part. Okay, so the next part we want to do is to explain why it's a point of inflection. Okay, so sometimes when we okay, this is just for illustration. So sometimes when we use the second derivative test, right? Okay, to find out whether a point is maximum or minimum. Okay, usually we will get d2y dx squared to be either positive or negative. So if d2y dx squared is positive, okay, so this is not part of the working for this question. If d2y over dx squared is greater than 0, then it means that the point is a minimum point, okay, if you recall. But if d2y dx squared is less than 0, then it means that the point is a maximum point. Okay, so let's try to find the d2y dx squared for this question. And then when we sub x equals to negative half inside, we see what we get, all right? So let's differentiate the dy dx again to find d2y over dx squared. Okay, so it's not difficult to differentiate using the chain rule. The 2 comes in front. So 2 times negative 6 becomes negative 12. Then 2x plus 1, reduce the power by 1. And then after that, you differentiate inside, get the 2. So you get negative 24, 2x plus 1. Okay, so over here, let's try to sub x equals to negative half inside. And then we see what happens to d2y dx squared, okay? So if x equals to negative half, okay, d2y over dx squared will be negative 24 times 2 minus half plus 1. Okay, so 2 times minus half will give you negative 1, right? Negative 1 plus 1 means this whole term becomes 0. Negative 24 times 0 means d2y dx squared is 0. So you can see if d2y dx squared is 0, we can't confirm the nature of the points, okay, the nature of the stationary point. Okay, so it may be a point of inflection, okay, which is what they want us to explain, right? It may be a point of inflection, but if d2y dx squared is 0, it doesn't mean that it's 100% a point of inflection. Okay, it may not be a point of inflection. Okay, so how can we prove that it's really a point of inflection? The only way is to use the first derivative test, okay? So if d2y dx squared is 0, then we can't confirm, then we need to fall back on the first derivative test. Okay, so if you recall for the first derivative test, we just draw a simple table over here. Okay, draw a simple table. Okay, then for here, okay, we divide into this way. Okay, then we divide into 4 columns. All right, so we divide into 4 columns. Okay, x here, dy over dx here, and this will be the graph. Okay, so now we are testing this point x equals to -half, right? So x equals to -half, dy dx is 0, so the curve will be flat. Okay, so now basically what we want to do is we want to test 2 points that is just before -half and after -half, and we want to see how the gradient looks like. All right. Okay, so -half is -0.5, so a point that's slightly less than it will be -0.6. A point that is slightly more than -0.5, maybe -0.4. Okay, so we are going to sub these two values, -0.6 and -0.4, into the dy dx. Okay, but you can see that we don't even need to do any calculation because dy dx is -6 times 2x plus 1 square, right? So no matter what x you sub inside, 2x plus 1, whatever number you compute out, you square it becomes positive. Okay, so this is always positive. Positive times a -6 will always give you negative. Okay, so no matter what value of x you put inside, dy dx is going to be negative. All right. So over here we will have negative and negative. So it's going to be this way, slope down and then slope down. So it's definitely going to be a point of inflection already because it's going to look like this, then flat at the x equals to -half, and then go back down. Okay, so it's neither a maximum point or minimum point. Okay, it goes this way. Okay, so how do we explain that it's a point of inflection? All we need to say is that before, okay, just before the stationary point, x equals to -half, the gradient is negative, and after the stationary point, the gradient is still negative. So it's going to be a point of inflection. Okay, so let's write down the answer. Since the gradient of the curve is negative before and after the stationary point, at x equals to -half is a point of inflection. Okay, so since before the stationary point, negative gradient, right, going down this way, after a stationary point, still negative gradient, so it's a point of inflection. All right. Okay, then there's a second part to this question. It's very easy. Write down the coordinates of the stationary point. Okay, so the equation of the curve is minus 2x plus 1 cube, right? Okay, so now at the stationary point, x equals to -half, correct or not? Okay, so if we sub -half inside here, okay, we will put -half inside here, x equal to -half. You have 2 times -half will be -1 plus 1. So this term is going to be equal to 0. Okay, so 8 minus 0 cube will be 8. So y is going to be 8. All right. So that's why they just say state or write down. Write down means you don't have to do any working. So you can say that stationary point, okay, equals to -half and 8. Right, so I've actually plotted this one using decimal, so we can actually go over and take a look. Okay, so over here. Okay, so you can see how the curve looks like. Okay, so this is a point of inflection. Before the stationary point, -half 8, okay, is negative gradient. After that, at the stationary point, it becomes flat for a while. and after that become negative gradient again. Alright, so this is a clear example of a question whereby the second derivative test is not sufficient for us to find the nature of the stationary point, because it's the second derivative test, d2y d squared is 0. So you need to fall back on the first derivative test. Alright.